Okay, so we have a smaller group than usual, but it looks like it's because there's a math midterm going on. And unfortunately, it looks like there's overlap again with our class, which is unfortunate. I did actually talk to the dean about not having tests from one class overlap another class. So hopefully they will fix these things in the future. So we are going to talk some more about energy today. I found this comic this morning, and since we're going to talk a little bit about pendulums today, I thought it was kind of entertaining. I apologize for anybody who's a psychology major here. So, and then the other thing I wanted to mention, can you guys hear me okay? Just make sure you can hear me okay. Is that, where is my share? Here we go. Is I wanted to mention that there's a new place to get help, and that's there's this new online study hall that just started up about a week or so ago. You can see the link down here at the bottom. And as you know, some of you have already found the math and science peer tutoring, which is great. But if you want someplace just to go and sit and study and not necessarily go one-on-one and ask a tutor questions, but just if you're the kind of person who likes there to be other people around when you're studying, because that helps motivate you, that's the idea behind the online study hall. And there will be experienced both science and math peer tutors and writing peer tutors available who will not necessarily provide tutoring, but can point you in the right direction if you have questions about resources available to you. So I just wanted to mention that. There's a whole bunch of other useful study skills things I put here together in this one module too that are worth looking at. Okay, so and then also just a reminder that I'm not going to do all those test adjustments until reading break. So please be patient and don't keep sending me emails about it. I'm not going to even look at them until next week because I have too many other things going on right now. All right, so let's have a look at what we're going to do today. Here we go. All right, so this is going to be our last lecture on energy, and we have a few more energy concepts to have a look at. Okay, so this is where we ended last time. We were looking at total mechanical energy, and we saw that if only conservative forces are doing work, which in our case would be the spring force and the force due to gravity, then this quantity that we're going to call total mechanical energy is conserved, which means during a process, this quantity doesn't change. So delta, it's a constant, basically, throughout the process. So, and so that means you can, and there's different ways to write it. You can sort of set the total energy at the beginning equal to the total energy at the end, E initial equals E final. Or you can look at the change in potential energy and the change in kinetic energy and see that the change in potential must be equal to minus the change in kinetic energy. So those are the two different ways. And so the first thing I wanted to do was do the thing I didn't get to do last time, which is to look at how this plays out in a situation where you have both gravitational and spring potential energy, like in the example of a vertical spring. And so we're going to go and look at a vertical spring now. So we're going to stop sharing that one. And we're going to go to our masses and springs PHYS. Wait for it to come up for you guys. So this is another one of these simulations. This one, that, like I said, is called masses and springs. And you can see down the bottom you have choices between intro, vectors, energy, and lab. So when we come back and do springs again later, this is a great one to come back and play around with. Today we're looking at the energy one because we're talking about various types of energy. And so what I'm going to do is I'm going to take this 200-gram mass and I'm going to hang it on the spring, and then I put it in slow motion so that you can see what happens. So it's going to oscillate up and down, and I've turned off the damping, which means there's no friction and there's no air resistance. And the thing to watch is this energy graph over here on the left, because now the total energy here, okay, is a sum of the kinetic energy of the mass when it's moving, the gravitational potential energy, and they've got their height equals 0 point right here. So right now the mass is above 0, so it's got some positive gravitational potential energy, and then the elastic potential energy because the spring is stretched. And you can see what happens, how the energy sort of sloshes back and forth between the different types, but the total always remains the same. So now I've reached a point where all of the energy is gravitational potential energy. There's no kinetic, which means the mass must be at rest, and there's no elastic, which means that the spring is neither compressed nor stretched. Okay, and then if you keep going, now it's going to go back down again. And so you can see how the three different quantities go up and down, but that constant, that total remains constant. So it's a nice illustration of how this works. Okay, so now we're going to stop sharing that one. We'll go back to our slides. So what I thought we would do now is do a question about this. All right, so I'll try and set up our poll here. Got 4 choices. Okay, so the question is, so we just did this with the PHYS. A mass is attached to a vertical uncompressed spring, which causes the spring to stretch and the mass to move downwards. What can you say about the changes in the spring potential energy and the gravitational potential energy of the mass? Okay, when this happens, when the mass moves downwards. So think about how you calculate both of those quantities and how they would change in this scenario. Sorry about that. So I lost my connection there, but I appear to be back now. So let's see if I can get this going again. So Okay, so I can still see the poll because the poll, I have two computers running simultaneously. So, and it looks like it's still being recorded. Hopefully that's the case. So hopefully we haven't completely lost the recording here. All right, so go ahead, and I think the poll's still working, so go ahead and keep guessing. We do get paid, but they don't pay us for the internet, so. All right, so let's try maybe 10 more seconds here. So go ahead and guess if you're not sure. Okay, 5, 4, 3, 2, 1. Let's see what everybody thought. Okay, so the largest group basically are going for B, that the spring potential energy increases and the gravitational potential energy decreases. And that's the right answer. Well done. How do we know? Well, if the spring is stretching, then that means an increase in spring potential energy, and if a mass is going downwards, then we know the gravitational potential is decreasing. So well done. So that means you have a great understanding of the basics of these different types of potential energy. So let's get rid of that. Okay, so I'm just going to double check this is still recording. As far as I can tell, this is still recording, so hopefully that's true. All right, so now what we're going to do is look at a simple pendulum. And we're going to say, is total mechanical energy conserved for a simple pendulum? Okay, so simple pendulum is just a mass on the end of a string or a rope, okay, that's free to swing. You usually pull it back at some angle theta and let it go. So what we're going to do is look at the forces acting on the pendulum bob. Okay, so what do we have acting on the pendulum bob? We have the tension of the string, and we have the force due to gravity, mg. All right, so to figure out if mechanical energy is conserved, we have to figure out, are there any non-conservative forces doing work? So we know that the net work would be the work done by gravity plus the work done by the tension. Okay, now in this case, the tension does no work. So a tension could be a non-conservative force if it were pulling an object, but in this case, because the tension is perpendicular to the displacement for the whole path, this is just like the ball moving in a circle. It's the same idea. Okay, because the tension is perpendicular, it does no work. So that means, yes, mechanical energy will be conserved. So we can learn things from that. We can use that fact to, for example, figure out how fast the mass would be moving at the bottom of the swing. So we know that because mechanical energy is conserved, that the change in gravitational potential energy equals minus the change in kinetic energy. So let's plug that in and see what we get. Okay, so when our pendulum is swinging downwards, okay, then what's our change in gravitational potential? Well, it's basically the final would be 0 because we set the bottom of the swing as y equals 0, and the top height would be h. So it's mg 0 minus h. And then similarly, the change in kinetic, the final kinetic energy would be 1/2 mv squared. The initial kinetic energy would be 0. So you just get minus 1/2 mv squared. And so you end up, you can solve that, the minus signs cancel, the masses cancel, and you get a nice simple result for how fast is the pendulum bob moving at the bottom of the swing. And its velocity, or the magnitude of its velocity, the speed, is the square root of 2gh. Okay, so it's the work, the tension is not 0. It's the work done by the tension that's 0. because the tension is perpendicular to the velocity. Remember, the velocity and the displacement point in the same direction, right? Velocity is just displacement over change in time. Okay, so for the entire path, right, the cosine of 90 is 0. So because tension and velocity are perpendicular, it does no work. All right, so now we're going to do another poll, and hopefully we won't lose it in the middle of this one. Where's my poll? And this one only has 3 choices. So this is based on a demo that I do when we're in the big lecture hall. Okay. And what's our question? The question says, we have a bowling ball and it's hanging from a really long cable in a lecture hall. And this apparatus is known as the super pendulum. And if the instructor raises the bowling ball to a height h and releases it from rest, what will happen when it swings back towards the instructor again? And you have to assume air resistance is negligible. So based on what we just learned about pendulums, what do you think will happen? So our choices are, it will rise to a height lower than where it started, it will rise to a height higher than where it started, or it will rise to exactly the same height h at which it was released. Those are our choices. And remember, we're assuming air resistance, friction, everything like that is negligible. So it's just a pendulum, and the only forces acting on a pendulum are the force due to gravity and the tension. Okay, maybe we'll do 10 more seconds on this one. So if you're not sure, go ahead and guess. Okay, 5, 4, 3, 2, 1. Let's see what everybody thought. All right, so what do we have? We have that the largest group by far thinks it's C, that the pendulum will rise to exactly the same height at which it was released. And then we have another group, a smaller group, that thinks it will rise to a height lower than the height where it started. So I can't do this demo for you, but a few years ago, somebody took a video of this. So this is me in one of the big lecture halls on campus, and hopefully this will work and you'll be able to see it. There is sound to this. I don't know if you're going to be able to hear the sound, but the sound at the end is kind of funny if you can hear it. So we'll play it one more time just for fun. So you can see that, in fact, I was okay with standing in front of the bowling ball like that, because the bowling ball does not go higher than it started. In fact, it goes, without air resistance, it goes exactly to the height it started at. There is actually a little bit of air resistance in the real world, so that bowling ball went slightly lower, but without air resistance, it goes back to the height it started at. Basically, total mechanical energy for a pendulum is conserved, so the initial energy equals the final energy, mechanical energy, and they're both equal to mgh. So it will rise to exactly the same height it started at. Okay, so now we're going to move on and talk about non-conservative forces. So if non-conservative forces do work, then total mechanical energy is not conserved. E mechanical will not stay constant throughout the process. So what do we mean by non-conservative forces? So basically friction, air resistance, any kind of propulsion forces, if you're pushing or pulling on the object, okay. Yeah, eventually air resistance will make things stop, and we'll see that too. Or if something's on a surface, friction will make things stop. Okay, so, but in fact, most of the forces we are going to run into are non-conservatives. The two biggies that are conservative that we've seen already are the force due to gravity and the spring force. Okay, so in this case, what happens? Well, in this case, you have to add an extra term. We're going to label the work by the non-conservative forces. And the idea is that if you start with a certain amount of potential energy, Ui, and you start with a certain amount of kinetic energy, Ki, then you have to add how much work the non-conservative forces do during the process. You add that to the initial situation, and then that's equal to the final values, the final potential energy and the final kinetic energy, the sum of those two. The other way to write it, if you rearrange this, is that the change in mechanical energy, okay, is equal to the work done by the non-conservative forces. Remember, before that quantity was equal to 0, but here it's not, okay? It's going to be either positive or negative. The other way to look at it, which they talked about in the pre-lecture, is to think about, because one thing we know is that energy is never created from nothing, and it doesn't ever completely be destroyed or disappear. Energy moves around and takes on different forms. It transforms. Okay, so another way to think about it is to say there's a change in potential energy, a change in kinetic energy, and there's a change in some other type of energy, and that when you add up all of those changes together, okay, it equals 0. In other words, the energy always is around somewhere. Okay. But when you add those three, if you go back and play around with the spring demo and you turn on the damping, you'll see the thermal energy, the heat energy there, okay, moving around, okay, but the total will still remain the same, okay. The other way, and then you can easily show then that the change in that other energy, whether it's kinetic energy or heat, is equal to minus the work done by the non-conservative forces. So let's look at an example that you've probably experienced in your life. You have an object sliding on a surface. It's moving with some velocity v, and like you push a book across the floor or something like that. You know what happens? It slows down and it stops, right? And why does it slow down and stop? Because of a combination of friction and air resistance. For, let's say in this case, we're only looking at the friction, right? Okay, so we know there's a frictional force, right? That's kinetic friction in this case because the object is sliding across the floor, and eventually the object's going to come to rest due to that kinetic frictional force causing a deceleration here, right? Causing it to slow down. And so what's the work done by the non-conservative force? In this case, it's the work by friction, okay? And in this case, we know that the work done by the friction is negative, right? How do we know that? Well, because the friction points in the opposite direction to the displacement. Okay, kinetic friction essentially always does negative work like this in a situation like this, okay? And then that means that that energy goes somewhere, okay? And where does that go? Well, it goes into heating up the surface and probably heating up the bottom of the object as well as it rubs against the surface, okay? And so what is the basically in this case the change in the other energy, the thermal energy, is equal to minus the change in kinetic energy. And we know that the change in kinetic energy here is negative, right? Because it slows down. So delta E other is a positive quantity, right? So there's positive energy going somewhere else. In this case, it's going into heat. I think we have time really quickly. Let's go back to, I wanted to show you that the spring thing again. I think we have time for this. So let's stop this for a second. Okay, so if we go back to our spring again, and now if I turn on the damping a little bit, actually, let's just reset it. I'm going to reset it completely. Okay, I'd like to have a big mass. Let's have a big mass. Okay, and now I put the mass on the vertical spring. Okay, and I pick it up. Okay, and I let it go. And you can see, again, that all of the energies add up to the total energy, but now we're including that energy other. In this case, it's thermal energy, okay? In this case, some of it's probably friction in the spring, but most of it's probably air resistance here, okay? And damping is the word for when something slows down, stops oscillating slowly and comes to a stop, okay? I'm gonna see if I can get this to go. And so you can, if we do it slowly, again, you can see the different energies going up and down. Okay, one thing to notice is the thermal energy only goes up. So the energy goes into thermal and you don't get that energy back again. Okay, there's not an easy way to get that energy back. Okay, so we'll stop that guy and let's go back to okay, so that was another example of where non-conservative forces are acting. So what we're going to do now, and for the rest of the class, is we are going to work our way through a complicated version of a situation where there are non-conservative forces acting. And what we're going to do is we're going to work on this together. So we're going to go through and I'm going to ask you questions as we go about the scenario. So let's have a look at where we're at. So we're going to have a block and it's being pulled up an incline by a rope. So you can see the block on the surface. Okay, there's a tension there, and notice that the tension makes an angle alpha with the horizontal. Okay, so that's one thing to keep in mind. There's friction on the surface, and we have a mu k equal to 0.25. And what we're trying to figure out is how fast is the block moving at height equals 1 meter. So when it gets to 1 meter vertically above the ground, how fast is it moving? Okay, and so they told us how big the tension is, 50 newtons. Alpha is the angle tension makes with the horizontal. Theta is the angle of incline. We've got a 5 kilogram mass, and we're starting at rest. So V0 equals 0. All right, so first part we're going to figure out. So this is our poll question number 3. Okay, so for this scenario, a block is pulled with tension T up an incline. The coefficient of kinetic friction between the block and the incline is mu k. What is the magnitude of the normal force? All right, so I'm going to start the poll on this one. So we've got 4 choices again. All right, so I'm going to give you some time to try and figure this one out. We're trying to figure out what is the normal force here. So I drew in a free body diagram there. Okay, so you can see all of our forces. We have the normal force. We have our, in sort of gray, we have the tension, which is green. Okay, we have the force due to gravity pointing downwards, our mg, so the weight of the object. And then we also have our kinetic friction that will appear as soon as the object starts moving, right? So as soon as it has a non-zero velocity, okay, we're going to have that kinetic friction pointing down the slope because our object's moving up the slope. All right, so that's our free body diagram drawn on top of the block, which is another way to do it, and that's fine if you want to do it that way. And if you have any questions, feel free to ask them. I'm thinking if the class size keeps staying smaller than 250, maybe one day we'll try and do this with breakout rooms, and we'll not use the webinar version of this. Okay, it looks like most people have answered. Maybe we'll do like 10 more seconds here. So go ahead and guess if you're not sure. Okay, 5, 4, 3, 2. Yeah, I like breakout rooms too. Okay, so I mean, you get to do them in tutorial, but I think with more than 250 people, I couldn't do them, but it looks like class has gotten to be smaller than that, so I think maybe next time we'll try that. All right, so why don't we have a look at the responses? But you should feel free to chat in the main chat if you have questions about things. I know it's not quite the same. All right, so what do we got? So we got the largest group are going for B, that the magnitude of the normal force is mg cos theta minus t sine alpha. But then we also have a reasonable number for A and D. Okay, so let's have a look at how you would figure this out. All right, so we already drew in all of our forces. So if we want to figure out the normal force, we need to look at what's the sum of the forces in the y direction. And just like with most inclined plane problems, we put the y direction perpendicular to the surface of the plane. Okay, so I'm going to start looking at my y components. So my y component of the gravitational force is mg cos theta. This always works the same way for inclined planes. And then the other force that's important to look at, we know we have the normal force and the positive y, but we also have a y component due to the tension. Okay, so remember I said this is a tension that's an angle alpha above the plane. Okay, so that means that there's a component of the tension, T sine alpha, okay, that's in the positive y direction. And then we go and we look at what is the sum of the forces in the positive y direction. So it's normal plus T sine alpha minus mg cos theta. And since there's no acceleration in the y direction, those three things have to add up to 0. And so that means that our normal force must be mg cos theta minus T sine alpha. You basically just solve for the normal force. This is how you always find the normal force. Look at everything perpendicular to the surface. Okay, look at all those forces perpendicular to the surface. Add them all up, set them equal to 0, and then solve for your normal, the magnitude. This is the magnitude of our normal force. Okay, so that means that the biggest group, well done, B, got the right answer. So are there any questions on that? How that works? And I don't have snow. I'm glad you guys have snow. Okay, so if there's no other questions on this one, we're going to do another one. Right now we're going to get slightly more complicated. Okay. Where are you guys located that it's snowing? Wow, okay, Burnaby, North Van. Oh, Maple Ridge, cool. See, I'm out by UBC. We don't have snow, unfortunately, out here. Not yet, at least. We had some the other day. Okay, so let's do our physics question now. So we have, again, a block is being pulled with a tension up an incline. The coefficient of kinetic friction is mu k. What is the work done by the non-conservative forces if the block moves a distance d up the incline? Okay, so that's what we're trying to figure out now. And we've got all of our forces here drawn in, okay, as we had drawn in the last clicker question, right? So you have to think about what are the non-conservative forces acting, and then figure out how much work they do. And then add up all those works to get the total work done by the non-conservative forces. So this one's a bit more complicated. So I'll give you a bit more time. Yeah, still no snow here. And it's probably worth writing this one down. And one thing to be careful about here is the sign of things. Okay. Think about which forces are doing positive work and which forces would do negative work. I don't believe some of the questions for the chapter 5-6 homework were changed or removed. They shouldn't have been. I'll go have a look at it. It shouldn't have changed. Someone might have changed it by mistake. All right, thanks, Isabel. I will check on it after class, make sure no one changed it. Okay, I think we're gonna try and have a look at this one now. Okay, so I realize these things get complicated fast when you start including lots of forces. So go ahead and take a guess about which of these you think might be the answer. Okay, 5, 4, 3, 2, 1. All right. What are non-conservative forces? So well, that's part of the question here, right? So why don't we have a look and see? So what do we have? So it looks like the largest group thinks the answer is A, and then we have the next largest group are voting for B. If you look at A and B, they're similar. They're just some sign differences there, right? Okay, so let's get rid of this poll and have a look. So we need to figure out the friction, right? We know friction is a non-conservative force for sure. Okay, so what is the kinetic frictional force? That's mu k times the normal force. We solved for the normal force in the previous question, and we saw that that was mg cos theta minus t sine alpha. So that means the normal force then is just mu k, sorry, the kinetic frictional force then is mu k times that quantity. So there's one non-conservative force. What's the other non-conservative force that's acting here? Does anyone know? There is one more non-conservative force acting. Anyone want to guess? Tension, yes, tension is non-conservative here. Tension has a component along the displacement. So here's an example where tension is doing work, non-zero work, and it's not. So it's a non-conservative force doing work. Okay, so what is our work? So it's a combination of the work done by the tension, which is the magnitude of the tension, the magnitude of displacement, and the cosine of the angle between the displacement and the tension vector, which is our cosine, which is our alpha, right? And tension is doing positive work because it's acting in the direction of the displacement. And then that's minus Fk, the magnitude of the frictional force, times d, the displacement, the magnitude of the displacement. Okay, and we know that that one has a minus sign because it's cosine of 180 degrees, right? The friction, kinetic friction point's opposite to the displacement vector. Okay, so then we just have to plug in that Fk then is mu k mg cos theta minus t sine alpha. You plug that in and you get that A is our answer. That lovely long expression, that is our work done by the non-conservative forces. Okay, so that's how you would figure that out. All right, so now what we're going to do is actually try and solve the problem. So this is where it gets fun because we're going to actually start manipulating. We're going to start doing some math basically and then plugging in some numbers now that we've done most of the physics. Okay, so where did we get to? So the question you might remember was how fast is the block moving when it gets to a height of 1 meter? So what's that speed there? Okay, what's the magnitude of the velocity? So I wrote down our work by our non-conservative forces again. We solved for in the last question. So we know that must be equal to the change in mechanical energy, total mechanical energy. So that must be equal to a sum of the change in the kinetic energy plus the change in the potential energy. And now there's no springs acting here, so the only potential energy we have to worry about is gravitational potential energy. And so we can actually figure out those two quantities quite easily here, right? The change in kinetic energy is 1/2 mv squared because it starts at rest and it ends up with a speed v. So that's a positive change. And it also goes up to a height 1 meter above the ground. So the change in gravitational potential is also positive. They're both positive, okay? And that one's equal to mgh. All right. So now we know that. Now we can start playing around. So we're after v, right? So the first thing I did was I subtracted mgh from both sides. Okay, so now I have 1/2 mv squared equals that long, lovely expression there. Okay, and then I can solve for v squared. I didn't solve for v because I didn't want to deal with the square root right now. We'll deal with that at the end. Okay, so basically just multiply both sides by 2 and divide by m. All right, and if you look at that long equation here, if you look at this, right, we know pretty much everything here, right? We know the magnitude of the tension, we know alpha, we know mu k, we know theta, we know the mass, we know g, we know almost everything. There's just one thing we don't know yet, and that's d. We don't know the displacement. Okay, we don't know that how far basically up the incline it goes, but that's actually pretty easy to figure out because we have a right triangle there, right? We know that d sine theta is equal to the height. So there's a relationship between the incline angle, the height, and basically the hypotenuse of that triangle. And so that means that d must be equal to 1 meter divided by the sine of the incline angle, which is 27 degrees. And that tells us that our magnitude of our displacement here is about 2.2 meters. And I kept a couple extra. I kept a 4th sig fig there, right? Because most of the quantities we were given, in fact, everything we were given to start with had 3 digits, 3 sig figs. So I'm keeping an extra one there. All right, so now it's just a matter of plugging in all our numbers. So that's what it looks like when you plug in all your numbers. Okay, and then being very careful about going through and doing the calculation. I usually do it in parts, okay? And then write them down on paper and then combine them. Trying to do it all in your calculator in one go, I think is a bad idea. Okay, so I just wanted to show you what it looks like, but I would recommend you do them part by part, like term by term. Figure out what 50 times 2.2 times the cosine of 13 is, write that number down with enough digits, you know, with like 4 digits. Do each part separately. Be careful with your minus signs. Okay, this is where things get hairy. Okay, I probably won't give you one quite this complicated on the test because there's a lot of potential for making math mistakes here. But if you're careful and you go through, and I'll let you try this at home and see if you get the same answer. When I did it, I got that this is in fact a positive quantity. That's good because according to what we're doing here, it should be positive. And it turns out that our block is moving at just over 4 meters per second when it gets to a height h. Okay, so that's what it would look like when you solve one of these problems. And then the other thing you can do to check, I didn't write this down, but one thing you can do to check your answer is to go through and calculate what is 1/2 mv squared, what is mgh, figure out those quantities, calculate the work by the non-conservative forces, and then set them equal to each other and see if it works. Okay, that's always a great way to check your answer. Okay, is to go back to your original equation here, take your v value, plug it in, and your h and everything you know, and see if the answer you get makes sense. So are there any questions on how that works? Any part of that was not clear? Okay, well, I'm happy to stick around and answer some questions, but otherwise, I think we're done for the day. So I hope everybody enjoys the snow if you have snow, and I will see you guys on Friday, where we're going to start a new chapter on Friday. Okay, we're going to stop recording here.